In this lecture, we'll look at linearization. The motivation is the following. All systems, dynamic systems that occur in nature are nonlinear. Nonlinear systems are difficult to analyze, and the course material that we'll cover in this course does not address this problem. You need to take advanced courses to solve nonlinear systems. More importantly, they do not have cookbook methods to solve nonlinear systems. You cannot use nice tools that you can in linear systems like Laplace transforms, cannot use root locus or Bode diagrams or other cookbook methods to design controllers. But within a small region of a given operating point, you can linearize a nonlinear system, i.e., generate or derive a linear version of a nonlinear system within a small region of the operating point. And there are abundance of mathematical tools to design controllers for linear systems. So linearization is a process of finding the approximate linear function at an operating point. Um, Here we'll introduce the general concept of nonlinear dynamic systems. We'll test for nonlinearity of functions. We'll look at Taylor series expansion and linearized nonlinear dynamic equations. We'll look at an abstract example uh, later. So let's try to understand what nonlinear systems are. Let's say you have a function of x, y, z, and many variables. Now it's a nonlinear function. You could choose a particular point x naught, y naught, z naught, whatever, uh, on this function, and find the tangent plane to the function. Now that tangent plane, if you look at the tangent plane within a small vicinity of this point x naught, y naught, here the tangent plane, which is the solid black line, is almost equal to the nonlinear function, which is the green line. So linearization is basically using the linear model instead of the nonlinear model within this small operating region. So let's say this function essentially defines the dynamics of some nonlinear system. The whole goal of linearizing the nonlinear dynamic system is to find uh, the linear dynamic system within the small region of the operating point, like so. Where is it used? Now if we look at so for example launching a rocket, a highly nonlinear system, it starts off and let's say this is the actual behavior of the rocket as it flies. What you could do is at the beginning, at the initial launch stage, you could say this is my operating point, and then find the linear approximation of the nonlinear dynamics. As the rocket goes up, let's say these two boosters go off, the operating point changes. Now we are at this operating point. Again, you find the linear model, the magenta line. You go further, you drop another stage, and then you end up with this red operating point. So over the life of this launch, you have say 3 operating points. Now what gain scheduling does is it designs linear controllers for each of these operating points and flips between one operating point to another depending on what stage the rocket in. So, and that's essentially the way they managed to launch the Apollo rockets to the moon with gain scheduling. So they linearized about various operating points and then started flipping the controller from one controller to the next as the rocket moved up. That's why it's kind of important. Now let's look at a test for linear functions. Linear functions have homogeneity and superposition properties. What is homogeneity? Homogeneity essentially says that if you have a function f of x, then f of alpha times x is equal to alpha times f of x, where alpha is a real number. Superposition essentially tells you if you have function f of x, if you want to find f of x1 plus x2, you replace x with x1 plus x2. That is the same as finding f of x1 and adding it to f of x2. Now these two together, homogeneity and superposition, and I'll illustrate that. If you have function f of x, if you want to find f of alpha x1 plus beta x2, where alpha and beta are real numbers, then that is the same as alpha times f of x1 plus beta times f of x2. So you could take any function f of x and see if it is linear or non-linear by applying this homogeneity plus superposition test. So let's look at an example here. F of x is sine x. We know that sine x is non-linear, but let's test it out. What is f of alpha x1 plus beta x2? It is sine of alpha x1 plus beta x2. So essentially I replace x with alpha times x1 plus beta times x2, and using trig identities we can expand this out like so. Now if I want to do alpha times f of x1 plus beta times f of x2, it ends up being alpha times sine of x1 plus beta times sine of x2. Now for linear function, if sine x was linear, then these two should be equal, but they are not. Therefore sine of x is not a linear function. How about the equation of a line ax plus b? Line, you would think that it is linear, but we'll show that it is not because of this constant here. The same test, superposition plus homogeneity. So you replace x with alpha times x1 plus beta times x2. It's basically a times this, which is a times alpha times ax1 plus beta times x2 plus b. And alpha times f of x1 plus beta times f of x2 will give you a times alpha times x1 plus b plus a times beta times x2 plus b, which is a times alpha times x1 plus a times beta times x2 plus 2b. These two are not equal, therefore this equation of a line is not linear. Now let's look at Taylor series expansion. Taylor series expansion is key to linearization. Taylor series expansion is an infinite series expansion of a function at a given point. When I say point, it's an operating point. The individual terms in the infinite series consist of derivatives of the function evaluated at the point and some polynomials. So it is essentially a polynomial representation of any function at a point. So let's look at a function of two variables. So if you have f of x and y, so you want to find f of x y about x naught y naught. So you are at x naught y naught, that's operating point, and you want to go a little bit away from x naught y naught by delta x and delta y respectively, and that is given by f of x y evaluated x naught y naught plus partial derivative of f of x with respect to x evaluated at x naught y naught times delta x plus partial derivative of f of x y with respect to y evaluated at x naught y naught times delta y plus 1 by 2 factorial. Now 2 factorial is 2 times 1, so n factorial is n times n minus 1 up to 1. So 1 by 2 factorial times the second partial derivative of f of x y with respect to x evaluated at x naught y naught times delta x squared plus same thing with delta y squared, and then you have this mixed derivative. So partial derivative of f of x with respect, first step with respect to x, and then with respect to y evaluated x naught y naught times delta x delta y. Now this is the constant term. These two guys here are the linear terms, first order terms, and these three guys, this and this, is the second order terms. So you can think how this will work if you have, say, more than two variables, three variables. Then if you have three variables, you will have this term, we'll have three of these terms, and however many of these second order terms. So let's look at an example. We want to find the Taylor series expansion of f of x y, which is x squared y, about the operating point 1 1. And we want it till the second order term. So we write a generic formula. So f of x naught plus delta x, y naught plus delta y. So we essentially replace x with x naught plus delta x, y naught with delta y, and that. Now that is nearly equal to f of xy evaluated at the operating point 1 1, partial of f with respect to x evaluated at 1 1 times delta x, partial of f with respect to y evaluated 1 1 times delta y, and all these second order terms as we showed before. If you put all the numbers in, if you do all the partial derivatives, now this evaluated at 1 1 is going to be 1, partial of this with respect to x, partial of this with respect to x is going to be 2xy, partial of this with respect to y is going to be x squared, and so on and so forth. And you evaluate these partial derivatives at the operating point, you end up getting 1 plus 2 delta x plus delta y plus delta x squared plus delta x delta y. This is the second order approximation of this nonlinear function about the operating point 1 1. Now you can use Taylor series to do just the linear approximation. What do you do with the linear approximation? You restrict the infinite series sum to the first derivatives only. So you just, in this case of function of two variables, you just take the first three terms. Function of three variables, you take the first four terms, and that's it. So for example, in our previous case, we would just take f of x, y evaluated 1, 1 and these two terms. So with delta x and delta y, nothing more. All the second order terms, we just drop them. That's the linear approximation with Taylor series. So if you work this out, you're going to get 1 plus 2 delta x plus delta y. So here we'll look at what does it mean to have linear versus nonlinear differential equations. We'll go through a series of types of differential equations. So first case is linear time invariant differential equations. Those are the equations that we love, and we'll work on these a lot in this class. They are of this form usually: ax double dot plus bx dot plus cx equal to u. U is the input, x is the dependent variable, u is the independent variable. A, B, C are constants. They don't change with respect to time. So if you have linear time invariant, you obviously are going to have linear time varying differential equations. What happens in these A, B, C now can be functions of time. Think of you're driving down the road in a car, and um, your car has I don't know, is losing parts. So over time, with the mass of your car changes, so that the differential equation that describes your car now would be of this form. And then you have nonlinear differential equations where these coefficients themselves can be functions of the dependent variable and its derivative. So a can be a function of x and x dot multiplied by x double dot, b is a function of x dot, and c is a function of x. Now if you look at robot dynamics, that equation would look like this.